today we're going to cover the material that we missed in class on Tuesday. So we're going to be going over chapter 5. This one has to do with chemical reactions. Okay. So the outline for this one is we're first going to go over chemical reactions and balancing equations, and then we're going to hit a little bit on recognizing types of reactions. Okay, so we're going to cover these 3 sections. And then the other 4 we will go over in class on Thursday. Okay, so let's get started with chemical equations. So this is an example of a chemical equation. It's an expression in which symbols and formulas are used to represent a chemical reaction. So basically what we're looking at here is right here I have one molecule, okay? And then here I have a separate molecule. So we have this carbon-hydrogen molecule and then an oxygen molecule. And then we put this plus sign to say that we mix them together in a certain way. And when we do that, it becomes CO2 and H2O. So that's a chemical reaction. We add 2 things together and they make different products. So let's go over what different parts of the equation mean. So you can tell that there is 2 sides of the equation. Right here, it kind of tells you where to stop or how to break it into the 2 sides. So that's going to be the arrow. So this left side of the equation is going to be called reactants. And the right side is going to be called products. Okay. So the reactants are the ones that you mix together. Products are the ones that you are making. Okay, and then we'll go over different parts of it in more in depth on the next slides. Okay, great. So on here we have a couple new things. So we have this heat here. So on the arrow, we're going to add anything else that was added to the reaction to make it happen. Sometimes it'll be heat, sometimes it'll be catalyst, things like that. And then on here, you can see that this has the reactants, okay? And then it has a definition for the reactants. Then on the right side of the equation, we have the products. And over here, you can tell that we have 3 different products, which is we can have different amounts of products. Most of the time it's going to be 2, but it can be 1 or 3. But these are the substances that are formed. Okay. Now, in this equation, you can see that here I have a number in front of it. And so this number is called a coefficient. Okay. So far, we've only really seen subscripts. So this one here, which tells us I have 3 O's, right? That subscript, that's what it tells us. This 2 here tells us that I have 2 of this whole molecule. So there's 2 NAs, 2 H's, 2 C's, and 2 CO3s. Okay, so that's what this is going to be. This is what it tells us, and that's called a coefficient. And then if it doesn't have a coefficient in front of it, like these 3 do, then we assume that the number is 1. Okay, so whenever it doesn't have a number in front of it, that means it's 1. Okay, but if it has a number in front of it, that's how many sets of the molecule you have. So now that we know a little bit about the equation, we can talk about balancing the equation. Okay, so the definition of balancing the chemical equation, or why we do it, is that it should indicate the appropriate amount of reactants needed to generate a given amount of products. And on here, we really use that idea that we learned before, which is matter is neither destroyed nor created. So whatever we have on the left side of the equation should also be on the right side of the equation. So for example, we're going to look at this equation and we're going to break it down piece by piece. So the first thing I like to do is I like to make these tables to be able to keep track of what I have on each side. Okay. So I'm going to start with this Na. So on the Na, I have one of it on the left side of the equation, on the reactant side. Okay. I have one hydrogen, I have one carbon, and I have three oxygens. As you can see right here, I have three. Oops. Okay. So now let's look at the right side of the equation. And let's see what we do and do not have here. Oh, I'm so sorry. Ah, there we go. That's what I meant to do. Okay, so for Na, I only have this one, but as we can see here, it has that subscript, so there's two of them. Okay, now for hydrogen, okay, you have to look at all the hydrogens, so that's going to be right here, and there's two of them. Okay, now for carbon, this one's a little bit tricky because there's multiple spots where carbon is found in the products. So carbon is here and carbon is here as well. So make sure to look at all of them and add them up. So we have one carbon here, we have one carbon here, so we have two in total. Oxygen is going to be similar in that we want to make sure that we count for all the oxygens. Okay, so we have this oxygen and this one. Okay, so here we have three, and here we have two. Oh, and look, I even forgot one. There we go. Okay, and then we have one there. So in total, we have six oxygens. Okay, so the whole point of balancing equations is I want to have the same amount of each element on the reactant side as I do on the product side. And if you look at this, I have one Na, I have two Nas. So as you can tell, they're not the same. So we need to do something to be able to balance it. Okay, so what we see is over here, everything is half of what it is over here. So how are we thinking about fixing that? We can just double the amount on the reactant side. And so that's where we add these coefficients, 2. So that way it doubles everything over there. So once we add in that 2, let's double check and make sure that it's still balanced. So Na, we now have 2. Hydrogen, we have 2. Carbon, we have, it looks like 1, but don't forget that we have 2 because there's 2 molecules now. And for oxygen, we have 3 times 2. Okay, so 3 times 2. So we have 6. So 6 oxygen total. So we are good on that one. And now we didn't change anything on the product side, so we just add it up again. So Na has 2, hydrogen has 2, carbon, let's do it in a different color just so we can keep track, has that and that, so there's 2. And then oxygen, we have this one, and this one. And let's clean that up so that we can see it better. Okay, so we have oxygen here, here, and here. Let's see, I have 3 oxygens here, I have 1 here, and 2 here. So add those up, and we have 6. So 6. And now, if you look at the products and the reactants, on how many of each atom there are, you can see that each of them have the exact same amount. And so this is what we mean by balancing equations. I want the same amount of Na on the products and reactants. I want the same amount of hydrogen on products reactants. So whatever is in the chemical equation should be on both sides of the equation, thus balancing the chemical equation. Okay. Okay, so over there is a definition of a balanced. It means the number and kinds of atoms must be the same on both sides of the reaction arrow. And then there's a little definition of coefficients. So this is a number placed in front of the formula to balance the chemical equation. And again, our coefficient's always going to be in front of it. Okay, and don't forget, if there is no coefficient, then we assume that it is 1. Okay, and whenever we're balancing equations, we're always going to use those coefficients to be able to balance it. We're not going to change any subscripts because if we change a subscript, we actually change the whole molecule. Remember the Lewis structures? If you change one thing on it, it's going to be a completely different structure. So that's why we only change the coefficients. Okay, and then if you noticed on our chemical equations, there's this little part, which is a parentheses, and then it has an S, and this one has a G. So let's talk about what those mean. So if you look here, each substance that is in the chemical reaction either comes in solid, liquids, gases, or is dissolved in aqueous solution. So this is actually important to know. So we usually notate this by putting it in parentheses and then putting a symbol or an abbreviation of what kind it is. So we have solids, liquids, gases, and then aqueous is AQ. And aqueous means it's something that is dissolved in an aqueous solution. And when we say aqueous solution, this is typically going to be H2O. Okay, so water. Okay, so now let's look at another example. So in the PDFs, it has steps on how to go about balancing an equation. And I really like the steps and I like how she did it because it walks you through it very well. So we're going to use one of her examples. So on here, on the left side, we can see we have our reactants. And on the right side, we have our products. So let's go step by step. So the first thing we're going to do is we're going to see how many carbons we have. So on the left side, on the reactant side, we have 3. You know what? I'm going to change colors because that's kind of hard to see. On the reactant side, we have 3 carbons. Okay, on the product side, however, we only have 1. Okay, so that's already going to be a little bit of a difference between the two. So we know we're going to have to balance that. So let's go to step 2. So step 2 is check the equation and make sure the numbers and kinds of atoms on both sides of the equation are the same. So we noticed that our carbons were different on the reactants and the products. So what we did is we added this 3 here to be able to make it so I have 3 carbons on both sides. So that's going to be how you balance them. You're going to see which one has more, which one has less, and how you can have them have the same amount. Okay, but once we do that, let's also check and make sure that we have the correct amount for all the other atoms. So let's look at hydrogen on the products on the reactant side. So over here we can see we have 8. And then for oxygen, okay, oxygen we have 2 here. So 8 and 2. Okay. Now on the product side, let's check it again, or let's check it as well. So hydrogen is right here, and I only have 2. I have 2 hydrogens there. Now oxygen, always make sure that you grab all the oxygen. So I have this one and this one. Okay. And then don't forget this coefficient applies to this oxygen as well. So I actually have 6 oxygens here. Okay. And then I have 1 here. So altogether I have 7. Okay. So as you can see, we do not have even numbers on hydrogen nor on oxygen. So we're going to have to think about how to fix that. So on here, how to fix that. And so we can look and see our hydrogens. I have 8 here and I have 2 here. So the way we can get them even is by timesing the products by 4. Okay, because if I have 2 times 4, that'll give me 8. So that's what I want. So I'm going to put a coefficient right here, which is 4. Now, let's go down here. We can see that we changed that coefficient to be able to help us with our matching our hydrogens. So let's double check and see if that worked. So the hydrogens over here is going to be 8. Oxygens are 2. Now on the product side, I have 4 times 2. So that's going to be 8 for hydrogens. So as we can see, that worked. We have a balanced amount of hydrogens now. Now let's check our oxygens. Okay, so oxygens, I have this one and this one. Okay, and so as we can see, I still have that 3 there. So don't forget about that. So there's 6 oxygens here. And then I have 4 times 1 oxygen. So this one's 4. Okay, and so we add that together. We have, oops, not 18. I have 10. There we go. Okay, so carbons are balanced, hydrogens are balanced. Last thing, I have more oxygens on the product side than I do on the reactant side. So how can I fix that? I can times my oxygen by 5. And I do that by putting a coefficient right here. Okay, so let's see if that coefficient helped. So now let's see, for our hydrogens, I still have 8. For our oxygens, I have 5 times 2, and that's going to be 10. Okay, and then on the product side, I now have, let's check the hydrogens. So I have that 4 times 2. So that's going to be 8 hydrogens on that side. And then for oxygen, I have this oxygen and this oxygen. So this one we're going to times by 4. So there's going to be 4 oxygens here. And this oxygen, there's 2 of them already. And then we times it by 3. So there's 6 here. And if we add those together, I have 10. So 10 oxygens. So if we check them, 3 and 3, 8 and 8, 10 and 10. So this is a balanced equation. So we've added the correct amount of coefficients to be able to have the same amount of each atom on both the products and the reactant side. So this is a balanced equation. Okay. Now, I know these squares don't work for everyone, but I really like it. And especially when you're starting, it's really nice to go step by step so you don't get lost. Because it's easy to like put a bunch of coefficients at the beginning and then not understand where you went wrong or why it's off. So just go step by step at the beginning, just change one at a time. So that way you can follow what you're doing. And then later on, you can skip as many steps as you want. Okay, and then step 3 is make sure the coefficients are reduced to their lowest whole number values. So let's use this one that we just did as an example. Okay, so let me copy and paste it. There we go. Okay, so let's say on this one, I decided to go crazy and I did 3 here, plus I did 15O2, and I did 9CO3, and I did 12H2O. Just because I got a little off and I tried different numbers. As you can see, these ones could be lower. I could just divide everything by 3, 5 by 3, and it would get me to these numbers. So as you can see, 3 divided by 3 is 1. 15 divided by 3 is 5. 9 divided by 3 is 3. And 12 divided by 3 is 4. So you're always going to want those lowest whole number values. Okay. So if you have something that's a little bit too high, just divide all of them by the same number, and that should get you to the lowest whole number. Okay. Okay. So, to be honest, this one is probably going to be some of the trickiest ones. These are called combustion reactions. And they're called combustion because we have a carbon group that is being lit on fire, and then it causes CO2 and water, usually in steam. Okay, so this is called combustion. And these ones are a little tricky just because the numbers get kind of big. Okay, so let's walk through this and see how we would do it. So on here, I have 4 carbons, and I have 1 here. Hydrogens, I have 10. I have 2 on this side. Then oxygens, I have 2. And over here, don't forget, I have it on 2 different molecules. So I have 2 plus 1, so 3. Okay. So I think the first number I want to fix is going to be this 4. So I'm going to put a 4 here to be able to get it to be at the right number. So I'm just going to cross this off instead of making a whole new box. Either way is good. I would probably make a whole new box just to not get confused, at least at the beginning. Okay, but now I have 4. And then the other number that changed is actually the oxygens. Okay, because as we can see now I have, for the oxygens, I have 8 over here. And I still have 1 here. So now, instead of 3, I have 9. Okay, now we need to fix the hydrogens. So for hydrogens, I have 10 here, and I have 2 here. So let's make those match. So I'm going to put a coefficient here of 5. So if I put a 5 there, now I have 10 hydrogens. And look, the 5 changes the oxygen again. So I'm going to cross out that 9 because I don't have 9 anymore. I have 4 times 2, so I still have that 8. Okay. And then over here, I don't have 1 anymore. I have 5. So 5 plus 8 equals 13. So now I have 13. Okay, so let's let's see if I'm missing anything else. Okay, so my 4s match, my 10s match, but now I have 2 and 13. So those don't quite match. Okay, now there's 2 tricks of doing this. You can do it one of 2 ways. One trick is you can do 13 divided by 2, which is kind of hard to see. 13 divided by 2. Okay, because then it does have 13, because 2 times divided by 2 means you get 13. But according to this rule, we want the lowest whole number values. We can't just have a half on there. So then what we can do is we can times all the coefficients by 2. Okay, so then I get 2C4H10 plus 13O2, which goes to 8402 CO2 plus 10H2O. Okay, so that's one trick that you can use. It's mostly going to be used on these combustion reactions, but it can be in other ones sometimes. Okay, so sometimes it's just a little bit easier to do a half and then times it by 2 later. Okay, great. Now here's some helpful tips um, that are given for balancing equations. So the first one is any element present in more than 2 locations should be balanced last. And that one's a great one just because those ones get a little tricky. So sometimes you want to do those a little bit later. And then any element which exists by itself in elemental form on one side of the equation should be balanced last. And this one's great. The thing is that one's going to be the easiest to balance just because you only have to change one number. So for example, on our combustion one, just barely, we left O2 to the very end. And that's because O2 is the easiest to balance. So that's why we left it to the end. So if there's anything by itself or bound to itself, then leave it to the end. It'll be much easier. Okay. If you can balance an equation by using fractions, do it. Then multiply by the denominator to get the whole number. So that's what we did with that combustion. We did the 13 halves, and then we times all of them by 2. Okay, and then last one for polyatomics. So polyatomics are a little bit tricky just because they're bigger, they add a lot more molecules or atoms. So sometimes it's just easier to keep to keep it together rather than separate it into different atoms. And I'll show you in a little bit. Okay, so for this one, this is tip 1, and so let's show you when it helps. So here it says any element present in more than 2 locations should be balanced last. So as you can see here, hydrogen is in 2 locations. Okay. Oxygen is in 4 locations. So that's a lot. So those are probably going to be the ones that we do last. Na, one location, or one location on each side. So that one's going to be a great one to start with. Okay. Or sulfur as well. Okay. Those are going to be the two that would be easiest to start with. But then again, this is a suggestion. You don't have to. Okay. So let's start with those. Okay. Hold on one sec. Okay. So on here, it looks like if we want to balance this one has 2 and this one has 1. So the easiest way is going to be putting a 2 in front of this one. Now we look here, we seem to have made a small mistake, so let's take that off. Okay, and let's check to see how we're doing. So on the reactant side, over here I have hydrogen, hydrogen, so I have 3. Okay, and now let's look at the sulfurs. So sulfur, I have 1 here, and so just 1. Oxygen, oops. Oxygen, I have this one, and I have this one. So over here I have 4, and over here I have 1. So when you add those together, I have 5 in total. And then for, oops, so I'm gonna have to redo them because I forgot about the coefficient. So hold on, let's redo them. Okay, so hydrogen. Okay, I have 2 here. Hydrogen over here, I have 1, but then I forgot there is that coefficient. So it's 2 times 1. So there's 2 over here. So there's 4 in total. Okay, don't forget those coefficients. They will mess you up. So let's check our sulfur again. I have 1. Okay, and then for oxygen, I have 4 over here. And then over here, I have 1, but then I have to remember there's a 2 there for the coefficient. So 1 times 2. Okay, so if I add those together, they come out to 6. And then for Na, there's only 1 of them, so that makes it nice. And then I have 1 Na, but then I have the 2 for the coefficient, so there's 2. Okay, now let's compare that to the right side of the equation and see if it matches. So let's start with H. So H, I have this 2 over here, so it's 2. Okay, for sulfur, I have 1. Okay, and then for O, I have this one and I have this one. So I have 4 here, 1 here, so that's going to be 5. And then Na, I have 2. So it's not quite balanced, it's almost there. So let's see what's not balancing. So the hydrogens aren't balanced. The sulfurs are balanced, which is great. The oxygen's not quite balanced yet. The NAs are balanced. Okay, so then last step, let's balance those out. So to get the correct amount of hydrogens, okay, I need to times this one by 2. So I put a 2 right here. Okay, I'm going to put that in green just so I can keep track of it. So 2. Now I'm going to renumber oxygen and hydrogen because those are the ones that are going to be impacted. And we're going to see if we have the right amount. So for hydrogens, I have 4, or 2 times 2, which equals 4. Okay, so I have 4 here. Now that matches. Okay, as we can see, we have 4 and 4. Perfect. Now let's check for our oxygens. For oxygens, I have 4 here. Oops, I accidentally erased that too. Okay, and then I have 1 times 2. Okay, and 4. So I have 6 in total. So 6. Now it's balanced because I have 6 on both sides. Okay. Now let's look at another example. So over here, again, so tip 2 on balancing the equation is any element which exists by itself on one side of the equation should be balanced last. Okay, so over here, Fe, so we can see iron is going to be all by itself. So we're going to leave that to last so that we can get the more complicated ones out of the way first. So over here, we're going to see what we have on both sides. So here I have 1, and then for chlorine, I have 3. On the right side of the products, I have 1 iron, and then I have 2 chlorines. Okay, so looks like we're doing pretty good. So for chlorine on the products and reactant side, I have 3 and I have 2. So the best way to be able to balance this is I'm going to times this by 2 to get 6. I'm going to times this by 3 to get 6, okay? Because I have to think about what's a common number that they can both make. So 6 is going to be the best one. So now I can add those coefficients in. So over here, remember, I need to times it by 3. So I'm going to put a 3 in front of the CL. And if you forget, just times that by that. So 3 times 2 equals 6. Okay, and what I want is 6, so I can match both sides. So that's good. That's going to be the coefficient I want. Okay, on the left side, on the reactant side, I want 6 as well. But now I have that 3, so I'm going to times it by 2. Okay, so now let's double check our coefficients. Okay, that's how many I had before. So let's double check after I add the coefficients. So I don't have 3 and 2 anymore. I have 3 times 2, oops, which is 6. So I have 6 over here. And over here, I also have a new value. So I have this 2 times 3, or 3 times 2, either way. So now I have 6 over here. So my chlorines are nice and balanced. But what was changed is actually the iron on the reactant side. Okay, we changed the coefficient to 2. So now instead of 1, I have 2. Okay, so they're not balanced anymore. But all I have to do is change the coefficient. I'm sorry, it's kind of messy, so let me clean it up a little bit. Okay, so all I have to do is change the coefficient of Fe. So I just added 2 here. Now I don't have 1, I have 2, and now they are balanced. So that's why we like leaving the 1 by itself to the end. It's just easier to add a coefficient to that without changing anything else. Okay, now for step 3, this one's the one that we did before. So as you remember, one tip that they give is doing the 13 and a half, having this and this. If you remember from the last one, that's what we had. And then multiply by the denominator to get the whole number coefficients. And right here, our denominator is 2. So we just times everything by 2 to be able to get the right numbers. Okay, so that's going to be the tip. And this is mostly going to be used for combustion. Okay. Oops. Okay. Now, last helpful tip is going to be with the polyatomics. So hopefully you guys remember the polyatomics. If not, just make sure to do a refresher on it and keep it in your memory. So on here, polyatomics, this is going to be our SO4, sulfate. So what we can do is we can just parentheses it, or at least in your head, parentheses it, so you can keep this all as one number. So over here, I can see I have 1 molecule of SO4. Okay, that way I don't have to count it as oxygens, I don't have to count it as sulfurs, I just keep it as SO4. And so I do 1 over here, and then I do everything else how I normally would. So Ca, I have 1. Okay, hydrogens, I'm going to count these hydrogens and these ones. Okay, so I can see I have 2 here, I have 2 here. So 4 in total. Okay, last one is going to be oxygens. Okay, so for oxygens, I have 1 here, and then don't forget to times it by the 2. So I have 2. Okay, let's check on the other side. On our products. So for products, that's supposed to be Ca, my bad. Okay, for Ca, I have 1. Hydrogens, you can see I have 2. Oxygens, I have 1 here. Okay, and the thing is, it would be hard to tell how many oxygens I had if I had to include this. So Not including, or sorry, having the polyatomic by itself is very, very helpful because now I can just say one. Okay, so now let's think about what coefficients we have to change to be able to balance this out. Okay, cool. Sorry, just had to see what I put on the next one. My bad. Okay, so let's clean this up. So let's balance out hydrogens first. Okay, so hydrogens, I have 4 here, I have 2 here. So I can just add a coefficient on the product side to be able to balance that out. Okay, so now let's see if it worked. So don't forget, I put a 2 here. So let's look at how many I have. I have 1, I have 4 hydrogens, I have 2 oxygens. Don't forget that coefficient. And then for our polyatomics, I just have the 1 here. Okay. Now, on the right side, on the product side, let's do those again. So 1Ca, don't forget that's a typo, my bad. Okay, for hydrogens, I now have 4. Okay, and then for oxygens, I don't have just the 1. I have 1 times 2, so it's going to be 1 times 2, 2. So I put the 2 there. And then for our polyatomic, we didn't change anything to it, so we still have 1. And now, if we double check our coefficient, or our how many we have on each side, we can see that they all match up. So our equation is balanced. So that's one really good tip. I really like this one because spreading out the polyatomics gets confusing, but if you keep it all together, then it's not as bad. Although, if that is confusing to you, you want to separate them, that's just fine. Okay, so now I would recommend try out the worksheet, try out section 1. There's a lot of balancing practice on there. The more you practice on this one, the better. If you watch me do it, it helps, but doing it yourself is where you actually learn to do it. So try that out. Highly recommend getting things wrong here and there because that's where you learn the most. And then let me know if you have any questions about it. Okay, and then we're going to cover one more section. So, one more topic. So we're going to do classifying chemical reactions. So in this class, we're going to learn the 3 main ones. So the 3 are going to be oxidation, reduction reactions. Okay. We're going to learn about precipitation reactions, and we're going to learn about acid-base reactions. Okay, these are going to be the 3. Now, so we're going to briefly go into each of them, get the main point of what they are, and then next class we're going to go more in depth. Okay, so this is going to be like a short version of it. Okay, so for classifying oxidation and reduction reactions, the main thing that we're looking for is we're looking for when elements either gain or lose electrons. Okay, now this is a little bit hard to tell if you don't know more about it, but when we go more in depth, you'll be able to tell a lot more. So for now, what you want to know is you want to be able to determine if something is an oxidation or reduction reaction just by looking at it. Okay, and the main things you're going to look at is you're going to look for neutral elements, okay, that make ionic compounds. So neutral elements is going to be like this oxygen and this magnesium. Okay, there's no charges on them. Okay, so they're neutral. Most of the time, magnesium, we're going to see it as 2 plus because that's how many electrons it needs to lose. However, sometimes it'll be in neutral form. And so that's how we can tell that something is going to be an oxidation and reduction reaction. Okay, the second type that we see is ionic compounds become neutral elements. Okay, so in the first one, we saw the reactants were neutral. On this one, now we see that the products are neutral. So Al, as you can see, it doesn't have a charge because it typically has that +3 charge. But on this one, it has no charge. So we can tell that it's going to be an oxidation reduction. Okay, and then the last one, covalent compounds are rearranged. This one, this one's a little bit harder to see, so don't worry about this one until we actually cover it more in depth. Okay, second one is going to be our precipitation reactions. So for this one, we're looking at solubility. We're looking to see if something dissolves or if it becomes a solid. So with this one, what we're really looking for is we're looking for aqueous solutions combine to form an insoluble compound. Okay, oops, insoluble compound. Okay, so that's going to be the main point. So right here, we can see we have AQ, we have AQ. And what that means is that it's aqueous solution, so it's something dissolved in water. Okay, and then this is the key point. Now we have a solid. Okay, we had AQs, those aqueous solutions, now we have a solid. And so it's going to look something like this. Okay, if you notice, this is a clear liquid, and we're pouring it into another clear liquid. But when we pour them together, all of a sudden there's this solid that forms. And so that's a precipitation reaction. It's two liquids being added together, making a solid. Okay, and then last one is going to be our classification of acid-base reactions. So acid-base reactions occur when H plus ions in solutions and OH negative ions in a solution combine to make liquid water. Okay, so those are the main things we're looking at. So in our example, first thing you're going to look for is the water. Okay, water is always going to be a good tell. But now we have to look at the reactant side and make sure that we have the H plus and the OH minus. So now these aren't always going to be, they're not going to be by themselves. They're going to be bound to something else. So here we can see we have this ionic compound. Okay, I have OH negative 1. So that's how I can tell there's my OH negative. How can I tell it's OH negative? One, it's a polyatomic, so we kind of have that charge memorized, but also we can see it's bound to iron. Iron is a metal, OH negative is a non-metal, so that's going to make an ionic compound. So we have 2 here, we have that iron, so we know that that's our OH negative. Now over here, we are going to have to memorize some acids, and H2SO4 is a very strong acid, so we're going to try to memorize that. So this is an acid telling us that this is going to give us that H+. So any acid is going to give us H+. Okay, and let's look at our second example and make sure that we understand why that's an acid. So, like the last one, first, let's make sure that there is a liquid at the end, an H2O liquid. Okay, and then let's look for our O negative and our H plus. So the O negative is going to be right here. Again, we can tell because it's next to a cation. Okay, and this will be our OH negative. Okay, those are typically going to be, those are always going to be in ionic bonds. So it's going to be bound to a cation. Now, HCl is going to be another strong acid. So that's how we know it's going to be H plus. Okay. Again, you won't be able to recognize the acids yet, but when we go more in depth on acids, I'll give you a list of the strong acids to memorize. You don't have to, but I promise it'll help a lot. So I would highly recommend that you do so. Okay. Now, on section 2 of the worksheet, try that out. On this one, you're just going to be recognizing what type of reaction you have. Is it acid-base? Is it precipitation? Or is it redox reaction? Just by what you know right now, just try to distinguish which one is which. And if you can't tell, no worries. Once we go through it a little bit more in depth, you'll definitely be able to tell. Okay, and then next time we'll go over more in depth on each of those reactions. So hopefully this makes sense. If you have any questions, please let me know, and I will see you in class on Thursday.